Okay, now I'm recording. Okay, perfect. All right. Yeah, so just to remind you very quickly, the definition of polynomial function. So we said, f of x is, a polynomial function is a function of the form, polynomial function is a function f of x is a function of the form. So we have so f of x equal to, and so we said we have like a combination of powers of x. So x to the power n. So the n, that will be the highest power of x, and in front of x to the power n there is some coefficient, a number, a subscript n. All right. And again, guys, the powers of x, they have to be positive or zero. Okay. So plus, etc. So you have all these powers of x. Then you have like x to the power 1 here, and then there's a constant a0. So all the powers of x are positive integers or positive whole numbers. Okay. Or 0. So again, powers, I mean, if you have like just one power which is not like a positive whole number or 0, then f is not a polynomial, right? So if you have some power which is like a rational, or it's a fraction, or you have some power which is a negative, some negative number, then f is not, it's not a polynomial. So all the powers, so what we have to keep in mind, guys, is that all the powers of x, they must be positive whole numbers or 0. 0 because, well, this constant here, the a0, you see this constant here, a0, this is just a number. So this is supposed to be times 1, but 1, again, it's like x to the power 0, right? This is x to the power 0, it's equal to 1, right? So that's why we say it's positive whole numbers or 0, because x to the power 0, that will be the constant. All right, so that's the definition. And then, yeah, we said, so in this section, we tried to, graph polynomial functions. I think I discussed at least one example on Monday. And then...
Patty, I'm gonna call you back.
Yep, okay, later, bye.
Okay, and yeah, so we had an exercise, as I said, on Monday. So I'm gonna do probably the first exercise. Okay, so this is from Monday. Yeah, so we have this following function f. So f of x is x to the 4th, I think, minus 6x cubed, right, plus 5x squared. Right. So first, we had to determine the behavior at infinity. So we have to determine the behavior at infinity. Okay, so what you're supposed to do, guys, first, you have to find the degree and the sign of the leading coefficient, right? So just to remind you, the degree, that will be the highest power of x. So first, so the degree, okay, I guess I have to mute someone. All right. Okay. Yeah, so we have to find the degree of f. And again, just to remind you, the definition, degree, that's the highest power of x. The highest power of x. So like in this example, the highest power of x, of course, would be 4. All right, so the degree is 4. Right, and 4 is an even number. Is even, right? Okay, so this is the first thing to do. Next, we need to find the sign of the leading coefficient. So the leading coefficient, that's the number or the coefficient in front of the highest power of x. So the highest power of x, of course, is x. It's 4, and in front of x to the fourth, well, there's supposed to be like 1 times x to the fourth, right? So my leading coefficient in this case would be 1. Leading coefficient is equal to 1, right? Again, so that will be this number here in front of the x to the fourth, in front of the highest power of x. All right, so 1, that's a positive number, right? This is positive. 1 is positive. That's positive. Okay, so we're gonna use these 2 pieces of informations that the degree is even and the leading coefficient is positive to find or to determine the behavior at infinity, right? Now, what you need to do, guys, I mean, you need to actually use the following table. So we have this table, again, so with the degree, so first column degree is even, second column the degree is odd, right? And then here first row leading coefficient is positive, is positive, and the second row the leading coefficient is negative. All right, so we said we have like 4 different cases, right? So again, it depends on the degree, if the degree is odd or even, and depends on the sign of the leading coefficient, if the leading coefficient is positive or negative. So for example, we said, well, if the degree is even and the leading coefficient is positive, so there'll be this case right here, then we're gonna have the behavior at infinity of the graph would be like something like this. Now, if the degree is even and leading coefficient is negative, right? So there'll be this case right here. The behavior of the graph would be like something like this. Now, if the degree is odd and leading coefficient is positive, so there'll be this case right here. Then we're gonna have something like this. And then finally the last case, when the degree is odd and leading coefficient is negative, right? The graph is gonna look like at negative infinity is gonna look like this. It's gonna be in the top, and at positive infinity is gonna be the graph. The output y is gonna be at negative infinity. Right, so we're gonna use this table or chart, okay, to find or to determine the behavior of our polynomial at infinity, right? So now we said our degree, the degree of our f is even, so we are like in this column, right? And the leading coefficient is positive, so that will be the first case, right? So that will be this case here. So this would be the answer. Okay, because this is when the degree is even and leading coefficient is positive. All right, so your answer, your final answer should be, so your answer is the following. So we're gonna have, so when x is at negative infinity, the output y is gonna be at positive infinity, and when x is at positive, the output is also, output y is also at positive infinity, right? So that's the answer. Does this make sense to you guys? Jimmy? Yeah, I got you, no problem. Thank you. Yeah, does this make sense to you guys? So you see how how to answer such a question, right? So in the test, of course, in the test or in the final, so probably you're gonna have to graph some polynomial function, right? So my advice for you guys is to, write down this table in your review in your formula sheet, okay, and then use it to determine the behavior at FNA. Okay. And again, this table here, it's not part of the answer. The answer is this one here. The answer is this, just this. This is your answer, okay? All right, so I'm gonna just probably erase this table because that's not part of the answer. I'm just explaining how I got the answer, right? And the answer is just this. Okay, okay, all right. Now, next, I think, so number 2, we have to find the x-intercepts and their multiplicities. All right, so to find the x-intercept, whenever you wanna find the x-intercept, you have to solve f of x equal to 0. That's how we find the x-intercept, always by solving f of x equal to 0. All right, so we need to solve f of x equal to 0. All right, so what's f of x? Well, it's the x fourth minus 6x cubed. So it's x to the 4th minus 6x cubed plus 5x squared, I think, equal to 0. All right, so as I said, I mean, as we discussed, I think probably on Monday and Wednesday last week. So the idea first, you need to try to find a common factor, okay? So as you can see in this polynomial, there's an x in here, x in the second term, and x in the third term, right? So then x would be a common factor, right? So, better than x, actually you can factor out x squared, right? Because there's an x in x squared here, there's an x in x squared in the x cube, and there's an x squared in the x to the 4th. So let's pull out the x squared times, to get this x to the 4th, you need to multiply x squared, of course, by x squared, right? You add the powers, 2 plus 2, that'll be 4, minus 6 x power 1, right? 2 plus 1, that would be the cube. And finally, plus 5. Right? So, again, guys, the idea is once you factor and you have a product, once we have a product equal to 0, all right, then you can deduce that one of the factors is 0. So either the first factor, this is my first factor, or my second factor is 0. Okay, so either the x squared is 0, or the x squared minus 6x plus 5 is 0. All right, so then x squared is 0. Of course, you just apply the square root both sides. So then it's just x equal to 0. Okay. Now, the question is, what's the multiplicity of this solution, right? We have this solution x equal to 0. So how many times is 0 solution of this equation, right? Because as you can see, I mean, x squared, this is like x times x, right? So either the first x is 0 or the second x is 0.
Professor.
Yes, yeah, please.
The fx, the last number is not 5, it's 9.
I think I changed it to 5 because 9, though, I'm gonna end up with very large numbers. So I prefer the 5. Yeah, I changed it. I think the last minute I changed it to 5.
Okay.
Mm-hmm. I mean, of course, we can do the 9, but the thing is, with the 9, we're gonna end up like with large solution. I mean, I think that we're gonna have like a square root, which is kind of annoying. Yeah, so it's better to take the 5. Yeah, so then this x equal to 0 is gonna be 2 times solution of this problem because of this square, right? X squared equal to 0. So in theory, you're supposed to end up with 2 solutions because of the square. But actually, we got just one solution, x equal to 0. So this x equal to 0 is actually 2 times solution of this problem because of this square again, right? So this multiplicity of this solution is 2. So multiplicity here is 2. Again, it's just because of this square. Okay. Now for the second equation, x squared minus 6x plus 5, and this is why I changed the 9 to 5, because, well, this is of course a quadratic equation, so we can use a quadratic formula, and then so your x, so it's minus b, so minus -6 plus or minus b squared, that's -6 squared, that will be 36, right? -6 times -6 minus 4 times a times c. Okay, so then over 2a, so 2 times 1. Yeah, so then your x would be +6 plus or minus, so square root of 36 minus 20, that would be 16, and so square root of 16 over 2. Actually, if I had a 9, well, it won't be bad. Well, anyway, it's fine. So 6 plus square root of 16 plus or minus square root of 16. Square root of 16, of course, that would be 4. 4 times 4 is 16 over 2. So then x is 6 plus 4 over 2. So that'll be 10 over 2. That'll be 5. Or x is 6 minus 4 over 2. So that would be 2 over 2, and that would be 1. So we got here 2 solutions, 2 different solutions, actually 5 and 1. And yeah, I mean, each of these solutions has a multiplicity of 1. So this is a multiplicity 1, multiplicity 1, and the same thing here, multiplicity 1. Right, because I started from this x squared minus 6x plus 5, so I'm supposed to end up with two different solutions, right? And I got exactly 2 different solutions, right? The 5 and 1. So each solution is just 1. 4 over 2 equal to 2. Where is it? Oh, you mean if I had the 9, Richmond? I guess, right? I didn't do any mistake here. I don't think I did a mistake. Yeah, if I had just a 9, yeah, actually, though, it's not that bad. Yeah. I thought I'm gonna end up with a kind of large number for my graph, but yeah, it's not that bad. All right, so the answer here. So we have 3 x-intercepts. So first we got the 0, and the 0, the multiplicity of 0 is we said it's 2. So 0, 0 with the multiplicity 2. We got a 5, the multiplicity 1. And then we have the 1, 0. Oh, sorry, multiplicity. Multiplicity 1. Right. So that's for the x-intercept, and then we
Excuse me,
have
Professor.
yeah, please.
So, when you said that the x equals 0 is a
Multiplicity
solution
2?
2 times, right?
Yeah, yeah.
So that means the x, wait, don't go.
Oh, sorry.
So that means with your x-intercept 0, 0, like, does it intersect 2 times at that point?
No, it means it doesn't, the graph, it doesn't cross the x-axis.
What?
So yeah, because when the multiplicity is even, so 2, this is even number, right? So when the multiplicity is even, your graph, it doesn't cross the x-axis. Actually, it's going to touch the x-axis at 0, 0, and then it's going to turn around. It doesn't.
Okay.
It doesn't
Wait,
cross the.
that's
yeah.
only when it's 2 times the solution.
Because it's even. For example, you can have like x to the 4th equal to 0, right? So then x equal to 0 would be of multiplicity 4, right? Multiplicity 4, for example, right? And that's, so 4 is even.
Right.
Okay, so then you're gonna have the same thing. You're gonna just touch the x-axis. You don't cross the x-axis. You touch the x-axis and then you turn around because the multiplicity is even. Okay. So all I'm saying is whenever the multiplicity is even, it's an even number, you don't cross the x-axis. You touch the x-axis and you turn around. When the multiplicity is odd, like here, 1 is odd, of course, then you're gonna cross, your graph is gonna cross the x-axis.
Okay.
So that's for the x-intercept, and then we need to find the y-intercept. And we need to find the y-intercept. In general, you need to evaluate f of 0, right? So f of 0, just plug 0 in the function f. What was my function f? X to the 4th minus 6x cubed. Yeah. All right, so it's 0 to the 4th minus 6 times 0 cube plus, I think, 5 times 0 square. So that will be, of course, everything is just 0. So the answer is 0. So yeah, so the y-intercept is just 0. So the answer, the y-intercept is 0. So it's 0, 0, of course. The first 0, that's because your x is always 0 in the y-intercept. All right, so then we can graph our function f, graph of f. So so we're gonna need, I guess, 0. So this is 0. We're gonna need the 1, and we're gonna need 5 actually. This is 5. Let's say 2, 3, 4, and then 5. This is -1, -2, etc. All right, guys. So first thing to do is you start with the infinity. right? So we're gonna use the answer to the first step. Remember for the behavior at infinity. So we said the graph is gonna start in the top right here, okay, on the left. So we're gonna start. Whenever you want to graph a function f, you always start from the left anyway. You always start from the left. So from the left at negative infinity, this is supposed to be, of course, this is like negative infinity right here, and this is like positive infinity. So you're gonna start from the top right here, okay? That's because of the behavior at infinity, right? And then at the end, so as you can see, you're gonna end up, the graph is gonna end up right here in the top. So so we're gonna have we're gonna have your graph right here. Okay, so that's for the behavior at infinity. Next, we need to plot our x-intercepts, right? We have the 0, 0, we have the 5, 0, we have the 1, 0. So this is my 0, 0, here's my 5, 0, and here's my 1, 0. Okay, and we need to plot the y-intercept, but the y-intercept is just 0, 0 again, right? So it's also the origin. All right, now all we have to do is just to connect all these points, right? So I'm gonna start from the top, from here. So next point would be the 0. That would be my next point, right? So we need to go to 0. All right. So when you arrive at 0, you touch 0, right? Then you have to decide whether you're gonna cross the x-axis or you don't cross the x-axis, right? And that's where you use the multiplicity, because we said the multiplicity of 0 is even, right? It's 2, so it's even, right? So we don't cross the x-axis. So here, at this point, here, so the multiplicity is even. Okay, so we don't cross the x-axis. So what I'm gonna do, I'm gonna just touch the 0, and then I'm gonna just turn around like this. All right, now next point is 1. So we need to go to 1. So I touch 1. Now, do we cross the x-axis? Well, multiplicity of 1, we said it's just 1. That's odd. So if multiplicity is odd, then we cross. So here, multiplicity is odd. So then we cross the x-axis. So we need to cross the x-axis. Okay, so I'm gonna go down. All right, so I cross my x-axis. Now, next point would be the 5. So we need to go to 5. All right, you arrive at 5. Again, 5, multiplicity of 5, it's 1. That's odd. The multiplicity is odd. So we need to cross. We need to cross the x-axis. So then we cross the x-axis, and then I'm done with my x-intercept. Right. So all I have to do now is just to go to infinity. Right here. Okay. So this is like the shape, I mean, the general shape of the graph. Of course, this is not perfect. It's not a perfect graph, but at least you get an idea about the graph, the shape of the graph. Any question, guys?
Yes.
Yeah, please. Yep.
All right.
Go ahead.
At the risk of sounding silly, how do I know when to stop when I cross?
To stop.
Like because when you came from the 1, right? You went down, you crossed the X.
Yeah, that's the thing. That's what I'm saying. So yeah, you're saying where do you stop? Here, right? Okay, so that's
and also at the 0 and between the 0 and the 1.
So this is yeah, you're gonna learn where to stop in Calc 1. Okay, so you need Calc 1. You need derivative. So this is Calc 1. Okay, in Calc 1
Just
you
don't
will
worry
see
about that right now, or
yeah, you don't worry about that right now. Yeah, because we don't have the tool to. I mean, we need the notion of derivative, and you're gonna learn derivative in Calc 1. So yeah, don't worry about it for now.
okay.
But it's a good point actually. That's very excellent question. And the same thing here. For like when you go up here,
Right.
right, and then you need to go to 1, so that you need to know where exactly you're gonna stop, right? That's the same thing. Yeah, absolutely. Good point. Any other question, guys? All right, so perfect. All right, so yeah, we are done with this section. Again, there are two more functions left, but they are very similar to this one. So I'm gonna just leave it as an exercise for you guys to think about it. So then I'm gonna move to the next next section. All right. Oops.
Wait.
Yeah. Yeah.
2 seconds.
Yeah, sure. So the next section, as I said, because we don't have much time, so I'm gonna try to do my best to cover everything, but I'm gonna focus, on the most important things. So I'm gonna jump to the section 2.6,
Okay, thank you.
where we're gonna graph rational functions. Oops, I don't wanna I wanna jump to a new page. Okay, I don't know what's going on here, but okay. All right. Yeah, so this is section. So I'm gonna jump to the section 2.6, rational functions. So after polynomial functions, we have the rational functions and their graphs. So now things gonna get a little bit more complicated, guys, because now it's not just like a polynomial, but like we're gonna have like a quotient of polynomials. So again, the idea, I mean, the goal of the section, of course, is to graph those rational functions. But let me first define what I mean by a rational function, right? So a rational function is just a quotient of polynomial functions. So a function f or rational functions are a quotient of polynomials. And so your function f, f of x is gonna be equal to p of x over q of x, where p and q are polynomials, where p of x and q of x are polynomials. Of course, so the domain of such function f, so the domain of f, well, because this is division, right? It's p of x over q of x. So we are dividing by q, right? This is division. So the domain of f, we need to exclude all the solutions of q of x equal to 0. So we need to exclude all the values of x where q of x is 0, right? So the domain of f, so we need to exclude all solutions to q of x equal to 0. Right, because the q of x is in the denominator, and we are not allowed to divide by 0, right? So for the domain, we need to exclude all the values of x where q of x is 0. Yeah, so examples, some explicit examples of rational functions. So examples. Right, so for example, f of x is equal to, let's say, x fourth minus 3x cubed, 3x cubed plus 2x squared minus 1 over, let's say, 5x to the power 7, minus x fifth plus x cubed minus x. All right. So as you can see, it's a quotient. So we have this fraction. In the top, that will be your polynomial p of x. So this is what I call p of x, the top, the polynomial in the top. That's my p of x, and in the denominator, that's my polynomial q of x. Okay, so it's p of x over q of x. Of course, the degree of p here, degree of p of x, the highest power of x in p of x, that would be the 4, right? It's 4 right here, so that's 4. And degree of q, the denominator, so the highest power of x in the denominator, that would be the 7, right? This is my 7. Okay, so again, it's p of x over q of x, where p and q are polynomials. Of course, I mean, you can have something which looks like, so for example, f of x equal to 2x minus 1 times, let's say, x plus 1 or x plus 3 over, x cubed minus 2x squared plus 4, for example. So let me just say here, guys, the top, the numerator, it's a polynomial, right? This is the top, it's a polynomial because all you have is just positive powers of x or or 0. But the question here is, what will be the degree of p of x? The degree of p, the highest power of x here, guys, so just be careful here. It's not 1. I mean, it looks like it's going to be 1, but it's not. It's 2, absolutely, Matthew, because because you need to distribute first. So I mean, your p is actually, so when you distribute, it's 2x minus 1 times x plus 3, so that will be equal to so 2x times x, that will be 2x squared, right? And then 2x times 3, that will be plus 2 times 3, that will be 6, so that's plus 6x. And then don't forget to multiply, do the same thing with this minus 1 or negative 1 times x, so that's minus x, and finally you multiply the negative 1 by the positive 3, minus 1 times positive 3, so that will be negative 3. Right. So as you can see, guys, I mean, this is kind of it's like a trap here, but the degree of p, the highest power of x, it's 2, it's not 1, right? Because when you distribute, you can see that the highest power of x is actually 2. So yeah, so the degree of p in this case, degree of p, it's 2. And degree of q, well, here it's straightforward, right? The degree of q, the highest power of x in the denominator. This is my denominator, that's my q, so that would be 3. All right. Yeah, so this is another example of a rational function. All right, and again, guys, so whenever you have, if you have some power which is not like a whole number, positive whole number, or a constant, or 0, I mean, then your f is not rational. So for example, if you take, let's say, f of x, and you have like x squared, minus 2x plus 1. Okay, this is good. But in the denominator, let's say you have like x fourth minus x to the negative 2, plus 2x. Okay. So here q, this is q, right? And here's your p. So just be careful here. This in this q, this power here, it's it's negative, right? And when you have a negative power, then your function is not a polynomial, right? So q here is not a polynomial, because of the negative power. So then your f is not, it's not, this f is not a rational function.
So like, what does that mean? Are we like dead in the water? Like what?
No, then then we are, yeah, I mean, you are done. It's not rational because, again, because the goal of this section is to graph rational functions. So if it's not rational, then yeah, you're done. All right. So yeah, as I said, yeah, the goal of this section is, so what we're gonna do now, we're gonna try to, so as we did for polynomial functions, we're gonna try to graph those rational functions, right? So the goal now, of course, is to graph rational, as we did for a polynomial. We're gonna graph rational functions. I would say graphing rational functions is more tricky than graphing polynomial functions. I mean, as you can expect, right? It's, it's a quotient. So yeah, we need to be careful. All right, so I'm gonna graph a couple of examples, very simple example of rational functions, and I'm gonna make a couple of observations about the graphs, and we're gonna use that to to graph our rational functions. So let me start with the first example. Example 1. Right, and I'm gonna take very simple rational function, which is f of x equal to just 1 over x. So 1 over x, why this is a rational function? Well, so we are supposed to have like a polynomials in the top, in the numerator and in the denominator, right? So the top, that's supposed to be my p of x, and the denominator, that's my q of x. Now, p of x, is it the polynomial? Yes. Remember, we said when you have a constant, that will be a constant. This is like x to the power 0. So p of x, p of x, it's 1, but you can write 1 like 1 times 1 if you like. So this is 1 times 1 is x to the power 0. Okay, so yeah, so then the degree of p, the highest power of x, is just 0. Okay, so the degree of p is 0. Yeah, so then 1 is a constant, it's a polynomial, right? We said that would be a polynomial of degree 0. Q, well, q of x, of course, which is x, and x is just x to the power 1. It's not power 0, it's power 1, right? So then degree of q is 1. Okay. So yeah, so then f is it's a rational function. It's the quotient of two polynomials. So f of x 1 over x is a polynomial. Is a rational function, right? It's a quotient of polynomials. Okay. All right. So before the graph, guys, I'm gonna make like a table of values. Well, before the table of values, let me just make one remark about the domain of f. This is a kind of important. So the domain of f f of x is just 1 over x. All right, so this is a division. So the domain, to find the domain, we need to exclude the values where the denominator is 0. Right, so we need to solve because this is a division, right? We have a division. So we are to find the domain. We are supposed to, whenever we have the division, we want to find the domain, you're supposed to solve denominator equal to 0. All right, so that's, well, denominator here, very simple. It's x equal to 0. Right? So the domain of f would be any real number domain of f would be any area number except the 0, because if x is 0, denominator is going to be 0, and we're not allowed to divide by 0. So the domain of f of x would be like, negative infinity, 0, excluded, union, 0, positive infinity. Okay. Now, what does it really mean that we exclude the 0? It means that f of 0, it's undefined. So f of 0, this is undefined. Okay, because 0 is not in the domain of f, right? We had to exclude 0 from the domain of f. So the output corresponding to 0 is undefined. So this is undefined. Okay, so 0 has no output. All right, that's what we mean by excluding 0 from the domain. It means that f of 0 is actually undefined. All right, now let's graph this 1 over x. So I'm gonna just take some values. So here's so let's graph now f of x. Okay, I'm gonna take some values of x. Okay, and let's say first I'm gonna be interested first in the in the graph of f when x is close to infinity. So for example, let's say your x is 10, then f of x 1 over 10, that will be 0.1. Well, we can start with 1. Let's say x is 1. So if x is 1, f of 1 over 1, of course, is 1. X is 10, 1 over 10, that will be 0.1. X is 100, then 1 over 100, that will be 0.01. X is 1,000, 1 over 1,000, that will be 0.001. 10,000, that will be 0.0001, etc. Right? So if you have like 100,000, that will be like 0.401, etc. So the idea here, guys, is, so as you can see, as x gets large, right? 10, 100, 1000, 10,000, etc. 100,000, etc. So here x is approaching infinity, right? X is getting large here. Okay, so here x is getting large, very large. Okay, so it's approaching, x approaches, it's approaching positive infinity, right? You think of positive infinity, again, positive infinity, it's not a number, but you think of it as like very, very large number. Okay, so x is getting large, so it's approaching a positive infinity. And on the other hand, the function f, the values of the function f, so as you can see, the values of the function f, they getting very, very small, right? 0.1, 0.01, 0.001, etc. Right? They're approaching. So as you can guess here, they're approaching zero. They're getting very, very small, right? They're approaching zero. So the values, your values of f, they are getting very small. Okay. So what we are saying here is that, so when x approaches positive infinity, right, f of x approaches zero. Okay, so again, the arrow, guys, means approaches or close to. X is in neighborhood or close to positive infinity, approaches. So then the values of f, sorry, the values of f, they approach, they're getting very small, smaller and smaller, and they're actually approaching zero. Right? So in the graph, guys, it means the following. So like this is one, I don't know, let's say this is 10, this is like 100, this is like 1,000, this is like 10,000, etc. So here, of course, you're approaching positive infinity. And say this is, of course, here's 1, this is supposed to be 0. So what we are saying is that, so of course, f of 1 is 1. And then we said, well, f of 10, it's 0.1, right? So it's going to be like 0.1 right here. That's going to be f of 100, like 0.01. So it's going to be very close. This is very, very close to 0, but it's not 0. Okay, so you have to keep in mind, so you're getting close to 0, but it's never equal to 0, actually. So the graph would be like the graph of f, it's going to be very, very close to the x-axis because they're supposed to getting close to 0, but it never touch. Okay, so here the graph, okay, the graph of f, it doesn't touch. The graph of f, it doesn't touch the x-axis, but actually it gets as close as you want from the x-axis, but it gets as close as we want from the x-axis. Okay, so again, guys, be careful here. There's no, you don't touch the x-axis. There's no intersection. There's no intersection here. There's no intersection. But you can get as close as you want from the x-axis. Okay, there's difference between touching the x-axis and getting as close as we want from the x-axis. Okay. So I mean, this line, this x-axis is kind of a special line, right? This line right here, I mean the x-axis, this blue line. It's a special because, again, because our graph, it gets very close to this blue line, but it never touched the blue line, right? Or the x-axis. And so such line, I'm going to define it later, of course. Where such line, so the x-axis, or the graph, let's say. So the graph of f, this is my f of x, of course. So the graph of f, sorry, of f, it doesn't touch the x-axis, but as I said, it gets as close as we want from the x-axis. So actually the x-axis is called the horizontal asymptote for the graph of f. So the x-axis, and I'm going to define it later after the examples, but let me just say, so the x-axis is called a horizontal asymptote. And it's called the horizontal asymptote because, again, it doesn't touch the graph, but the graph actually gets as close as we want from the x-axis. So that's why it's called the horizontal asymptote. All right. So this is when the values of x approaches or approach infinity, right? When x approach infinity, right? Your values of f approach 0. Now let's see what happens when the values of x approaches 0. So just to remind you, f of 0 is undefined, right? We said f of 0 because 0 is not in the domain. So this is undefined, right? F of 0 is undefined. What I'm going to do, I'm going to take some values of x, which approach 0. So here's your x. Here's your, again, f of x. And instead of approaching infinity, I'm going to try to approach 0. So the values of x are going to approach 0. So for example, you start from 1. Of course, 1 over 1 would be 1. If x is 0.1, f of 0.1, that will be 1 over 0.1. That will be 10. If x is 0.01, 1 over 0.01, that will be 100, etc. Be 1,000 here. That will be 10,000. You know. So as you can see, as x approaches 0, as the values of x get very small, the values of f of the function f, they're going to get very large. This is, I guess, 100,000. Okay. So the idea here is that here x, the values of x, they approach 0. Of course, x cannot be equal to 0, right? Because f of 0 is undefined, right? So here, very important remark, x cannot be 0. Okay, that's because 0, it's not in the domain. So f of 0 is undefined. All right, you can approach 0, but you cannot be equal to 0. That's what I'm saying. Now, for the function f, the values of the function f, as you can see, they get very, very large, right? So they approach actually infinity. They're approaching infinity. Okay. So yeah, so I'm gonna just write it down. So what we are saying is as x approaches 0, right? F of x approaches positive infinity, right? So now what does it mean this for the graph of f? Let's see what happens to the graph. So of course, here's my positive infinity. This is 0. So I need very small values of x, right? Like 0 0.1, 0. So let's say this is like 1, 0 0.1. You know, it's supposed to be like, I don't know, like here. I'm just taking some examples here, guys. I mean, I'm not. So this is like 0 0.01. You know, the values of x they are very close to 0, right? Now, on the other hand, the values of f, so here's, let's say 1, I don't know, let's say this is like 10, this is like 100, this is like 1000, you know, etc. So what we are saying is, so the graph is going to be like f of 1, of course, is 1, 1 over 1 is 1. When x is 0 0.1, that will be 1 over 0 0.1, that will be 10. So it's going to be like somewhere right here. When x is 0 0.01, f of x would be like 100, you know, etc. Then 1000. You're getting close to 0. The values of f, they're gonna go up, right? So you're gonna go like, you know, like 1000, 10,000, 100,000, etc. Right? You're gonna be very close to the y-axis. So the graph would be like, the graph of f would be like, so you're gonna go up, all the way up, because the values of f, they're gonna go to infinity, right? We said f is getting very large, right? So then the values of f, they're gonna go up. But the thing is, you don't touch this y-axis. Okay, your graph of f, the graph of f doesn't touch the y-axis. And the reason is, well, it's because f of 0 is undefined, right? Remember, we said f of 0, this is undefined. Right, so which means that if your x is 0, there's no corresponding output. So which means that the graph of f, it doesn't touch the y-axis. So because if the graph of f, you know, if the graph of f touch the y-axis, you know, like here's 0, and I don't know, your graph of f touch, you know, your y-axis, then let's say this is like, I don't know, 1 million, right? You touch the y-axis at 1 million. Well, it means that f of 0 is going to be 1 million, right? If you touch the y-axis. But the thing is, f of 0 is undefined. So you're not supposed to touch the y-axis, right? So the same thing here with the y-axis. So there's no intersection between the graph and the y-axis. So no intersection. Between the graph of f and the y-axis, right? But the thing, of course, that is that you can get the graph of f as close as you want from the y-axis. So the graph of f is as close as we want from the y-axis, but never touch the y-axis. Okay. So yeah, and again, the reason is f of 0 is undefined, so you cannot touch the y-axis. So such such a line like this y-axis is actually called a vertical asymptote. As we said, so as x values of x approaches 0, the values of f approach positive infinity. So then the y-axis is actually called a vertical asymptote. Okay. So yeah. So as you can see, for this graph of 1 over x, we have like two things. We have this, this x-axis, which is actually what I call the horizontal asymptote. So my graph is going to get as close as I want from the x-axis, but never touch the x-axis. And the same thing with the y-axis. So, and actually this y-axis is called the vertical asymptote. So before the definitions of horizontal and vertical asymptote, so let me just now graph this f. So the graph of f would be like, so graph of f of x equal to 1 over x. So we're going to have like something like this here. So yeah, so this is supposed to be 0, of course. Of course, this is positive infinity. This is negative infinity. Negative. So as we said, here, so the graph of f is gonna be as close as I want from the x-axis, but never touch the x-axis, right? And then the same thing here for the y-axis. I'm gonna get as close as I want from the y-axis, but I won't touch the y-axis, right? So again, here, no intersection, and no, so there's no intersection. All right. Now for the negative values, the same thing. So we're gonna have like here, I'm gonna get as close as I want from my x-axis, but I won't touch the x-axis. And the same thing here, I'm gonna get as close as I want from the y-axis, but I don't touch the y-axis. Okay, so here the same thing. There is no intersection. No intersection. All right, and as I said, so this y-axis, is going to be called a vertical asymptote. So yeah, so let me before the next example, guys. So I'm going to define now a vertical asymptote. What do I mean by a vertical asymptote? And then I'm going to explain exactly what do we mean when we have a vertical asymptote in the graph. Okay, so yeah, so let me define first this notion of vertical asymptote. And I'm going to show you how to find the vertical asymptote. So in this example, of course, 1 over x, my vertical asymptote is given by this. It's a vertical line, right? When I say vertical asymptote, it's a vertical line. It's given by the y-axis, but of course, it's not always the y-axis. So the vertical asymptote is going to depend on the graph. All right, so let me define now what I mean by a vertical asymptote and how do we find a vertical asymptote. So definition. So a vertical asymptote, it's a vertical line. So a vertical asymptote is a vertical line, okay? And so the equation of this vertical line, let's say x equal to a, okay? So for example, for this y-axis, my y-axis. So what's the equation of the y-axis? Well, it's, you know, all the points on the y-axis, the x coordinate is 0, right? So if you take any point on the y-axis, you know, for example, this point right here, the x coordinate is 0. The x coordinate of this point is also 0. So all the points, the x coordinate of all the points on the y-axis, just x equal to 0, right? So the equation of the y-axis is x equal to 0. Okay. Now, a vertical asymptote in general, it's a vertical line with the equation x equal to a. Okay, it means that it passes through the x equal to a. Like here, the y-axis, it passes through the, you know, the point with x equal to 0. So it's a vertical line, x equal to a, which satisfies the following. So it satisfies the following. So remember what we said about this y-axis here. You know, we said as x approaches 0, you know, the values of x approaches 0, the values of y, they're gonna approach infinity, right? So we said as x, you know, approach 0, f of x is gonna approach infinity, right? You know, for example, here's your x, it's close to 0, and as you can see, the f of x, the output, corresponding output, is very large, right? So yeah, vertical asymptote satisfies actually the following. So as x approaches a, so in our example, a would be 0. So as x approaches a, f of x approaches, well, either positive or negative infinity, right? Because as you can see here, here in the bottom, it's the same thing, right? My x approaches 0 from the left. You know, x is negative. So the values of f, they're gonna approach negative infinity. Okay. So as x approaches a, f of x is gonna approach either positive or negative infinity. Okay. So the idea here is the following, guys. So what happens when we have a vertical asymptote? So we're gonna have the following in the graph. So let's say this is x equal to a. Here's my x equal to a. Okay. And if you have a vertical asymptote x equal to a, then we're gonna have the following. So we're gonna have this, you know, this vertical line passing through the x equal to a, right? Because the equation is x equal to a of the vertical asymptote. And then the graph is gonna be the graph of f. The values of f, as you can see, they're gonna approach either positive or negative infinity, right? So of course, this is my positive infinity right here. This is my negative infinity. So as x approaches a, so I'm approaching a. So like x would be like in the neighborhood of a, like this is the green neighborhood, you know, of a. The values of f, the corresponding values, the corresponding outputs, you know, they're gonna approach positive or negative infinity. So we're gonna have something like, so the graph is gonna look like, so the graph is gonna be like this here. Okay, or at negative infinity. So you're gonna have like something like this here. Okay, and again, the idea is that the graph of f, it doesn't touch your vertical asymptote, right? This is f of x. So the graph of f, it doesn't touch the vertical asymptote, but it gets as close as you want from the vertical asymptote, right? So there's no intersection. So there's no intersection between the graph and the vertical asymptote, but the graph, of course, but f gets as close as we want from the vertical asymptote. Okay. Of course, either at positive infinity or at negative infinity. Okay. So that's what we mean by a vertical asymptote. So whenever you have a vertical asymptote in the graph, then this is what happens, right? Your graph is gonna be like as close as you want from the vertical asymptote, but there will be no intersection. Okay. So that's my vertical asymptote right here, and here's my graph. Okay, very close, but doesn't touch the vertical asymptote. All right. Well, of course. So this is for the vertical asymptote. We're gonna have the same thing for a horizontal asymptote. But before the horizontal asymptote, let me just show you guys how to find the vertical asymptotes. So given a rational function, how do we find vertical asymptotes? So now the question is, so given a rational function f, so how do we find vertical asymptotes? Of course, you can have like more than one vertical asymptote. So let me just come back to my example, 1 over x, right? So we said for 1 over x, so this is the graph of 1 over x. We said like this, the y-axis, that will be my vertical asymptote, right? X equal to 0. So the y-axis is my vertical asymptote. And remember, 0 was excluded from the domain, right? And that's actually the reason why my graph, it doesn't touch the y-axis, because f of 0 is undefined. So you're not supposed to intersect the y-axis or the x equal to 0. So to find, of course, 0, we had to solve the denominator equal to 0. And that's how we find vertical asymptotes in general. All we have to do is just to solve the denominator equal to 0. Okay, because that's the values that you exclude from the domain, right? So to find vertical asymptote, all you have to do is just to solve. So if you have f of x equal to p of x over q of x, so all we have to do is to solve. So solve q of x, denominator equal to 0, to find vertical asymptotes. So just solve the denominator. We'll solve the bottom denominator. Just solve denominator equal to 0. The denominator. All right. So that's how we find the vertical asymptote. Any questions so far, guys, about the vertical asymptote? As I said, this section kind of tricky. Rational functions, there are some, I mean, they're not easy to graph because of this vertical asymptote and horizontal asymptote. But we're gonna try to do like a lot of examples, of course. Yeah, but yeah, so that's the definition of vertical asymptote. And again, all you have to do to find vertical asymptote, just to solve denominator equal to 0. Now, for the horizontal asymptote, there's a good news. The good news is that you cannot have more than one horizontal asymptote. Okay, either one horizontal asymptote or zero or none. Okay, but before that, let me define and explain how we find the horizontal asymptote. So now for the horizontal asymptote, so remember in our example with 1/x, our horizontal asymptote was the x-axis, right? The x-axis, yeah, right. So this is my horizontal asymptote. It's a horizontal line, right? And what happens is that my graph is gonna be very close as I want from my horizontal asymptote, right? But again, there will be no intersection. And this happens actually at infinity, either at positive infinity or negative infinity, right? When your x is at negative infinity or positive infinity, right? Yeah, so a vertical asymptote, a horizontal asymptote is a horizontal line, of course, is a horizontal line. And so what's the equation of the horizontal line? So for example, here I have the x-axis. So what's the equation of the x-axis? No, if you take any point on the x-axis, the y-coordinate is going to be 0, right? All the points on the y lying on the x-axis, the y-coordinate would be 0. So the equation of the x-axis is just, y equal to 0, right? Because if you take any point, the y would be 0. Okay, so it's a horizontal line given by, the equation is actually y equal to, let's say, instead of a, I'm going to use a different letter. I'm going to use, let's say, L. Okay, so satisfying the following. So remember, my x was for the horizontal asymptote. My x was in the neighborhood of infinity, right? My x was approaching infinity, right? Your x is, it's just right here. So you are approaching negative or positive infinity for the horizontal asymptote. So as x approaches either positive or negative infinity, your f of x is going to approach this number here, L. Okay, so like here for this 1/x, as x approaches, for example here, x approaches positive infinity, x gets very large, the values of f, they're gonna be close to 0 or L. Okay, so the function, the values of f are gonna be close to some number, like in this case that will be 0. Yeah, so this is definition of horizontal asymptote. As x approaches positive or negative infinity, your f is going to approach L. So the idea is the following, guys. That's the definition, but let's see what this means for the graph. So we have like, here's your graph, and we have this line L. So y equal to L, right? So this is a horizontal line, right? So L, let's say here's my L, y equals to L. Right, this is my y-axis again, right? So y is equal to L. So there'll be a horizontal line. So it's going to be this line here. So this is y equals to L. Okay. Now, if what we are saying is that, so if x is a neighborhood of negative infinity or positive infinity, so your x is like somewhere right here, close to negative infinity or close to positive infinity. So what we are saying is that the values of f, they're gonna be close to L. So the graph of f is gonna be close to this line L, y equals to L. So the graph is gonna be like, we're gonna be close. All right, it doesn't touch, again, it doesn't cross this line, y equals to L, but it's gonna be as close as we want, right? So, or it can be in the other side, right? So something like this here, or at positive infinity. So it's gonna be, your graph is gonna be below the horizontal asymptote, or of course above the horizontal asymptote. Very close to the horizontal asymptote, but of course there will be no intersection, right? So here, as you can see here, again, there is no intersection, right? No intersection. But the graph f is going to be close, as close as we want, from the horizontal asymptote. Okay. So that's what we mean by the horizontal asymptote. As I said, as a good news, there will be at most one horizontal asymptote. Okay, so either one horizontal asymptote or none. Okay. Now the question, of course, how do we find horizontal asymptote? Because like in our example, 1/x, the horizontal asymptote was like the x-axis, and that's y equal to 0. But actually, it's not always the horizontal asymptote. It's not always the x-axis. So it can be a different line. Now, how do we find this horizontal asymptote? So the question now. So how do we find the horizontal asymptote of f of x equal to p of x over q of x, right? My rational function f, and I want to find the horizontal asymptote. Well, they're going to be like 3 different cases. So if, so first case, so it depends actually on the degrees of p and q. So if the degree of p is larger than degree of q, okay, then actually there will be no horizontal asymptote. Then there is no horizontal asymptote. Okay, so if the degree of the highest power of x in the top is larger, strictly larger than the highest power of x in the denominator, then there will be no horizontal asymptote. Okay. The second case, and I promise, guys, after this we're gonna do a lot of examples. All right. Case number 2. If degree of p of the top, degree of the top is less than the degree of denominator. Okay, then this is exactly like our example 1/x, right? 1/x, we said this is like p, of course. This is like q. So degree of p here is degree is 0. right? This is because it's x to the power 0. That's 1. Degree is 0. And here degree is 1, right? This is x power 1, right? So degree of P is less than degree of Q. 0 is less than 1, of course. And the horizontal asymptote we had is the x-axis, and that's y equal to 0. So then in this case, the x-axis is going to be the horizontal asymptote. So the x-axis is the horizontal asymptote. Then the x-axis is the horizontal asymptote. Okay, again, this is y equal to 0. The equation is y equal to 0. Okay, so this is like the 1 over x. The x-axis is going to be horizontal asymptote. Last case is when the degree of P is equal to the degree of Q. If they have the same degrees, so K is 3. So if a degree of P is equal to the degree of Q, then the horizontal asymptote is going to be given by the ratio of the leading coefficient. So then the horizontal asymptote is y equals 2. So leading coefficient of P over the leading coefficient of Q. Okay. All right, so we have like 10 minutes left. So let's do an exercise where we have to find like the horizontal asymptote and the vertical asymptote. And then the next time, because now we don't have time, in 10 minutes, it's not enough. But next time I will show you how to use all the informations, the vertical, horizontal asymptote. We're gonna use the x-intercept, y-intercept, etc. to graph our rational functions, okay? So, but in the last 10 minutes, guys, I'm gonna just try to find like as an exercise. So an example, let me first do an example. And so let's take f of x equal to 2x fourth minus 3x cube plus 2x over, let's say 5x fourth minus x cube plus 2x squared minus 1, right? And let's say I want to find the vertical asymptote and vertical and horizontal asymptotes. So for the vertical asymptote, I should probably here, sorry, I should probably change this a little bit, make it easy to solve. So let me just say this is actually 5x fourth minus 3x cube plus minus, let's take minus again, minus 2x squared. Okay. So yeah, so So the top, this is my P of X. The denominator, it's my Q of X. All right, this is, of course, this is a rational function because P and Q both are polynomials, right? So first, let's find the vertical asymptote. Find vertical asymptote. So to find the vertical asymptote, guys, I mean, basically what all you have to do is just solve denominator equal to 0. All right, so we need to solve denominator equal to 0. Okay, that's all you have to do. So just be careful because the next time, of course, when we graph these rational functions, we're gonna need to find the x-intercept. Okay, and we'll see to find the x-intercept, like when you have a rational function, we'll have to solve the numerator equal to 0. So that's different from, of course, the vertical asymptote where you have to solve the denominator equal to 0. Anyway, so we're going to discuss this next time for the x-intercept. But for the vertical asymptote, it's the denominator. Okay, it's the denominator equal to 0 for the vertical asymptote. So that will be the 5x to the fourth, minus the x cubed minus 2x squared, equal to 0. And as we did like for the polynomials, you have to find the common factor. That will be the x squared in this case, so this is x squared times 5x squared minus the x minus 2 is 0. So so either the x squared is 0 or 5x squared minus the x minus 2 is 0. So x squared is 0, you apply the square root, so that's just the x is 0. Here you don't have to worry about the multiplicities here, guys. Okay, for the rational functions, all you have to do is just solve. Here x, you apply quadratic formula, right? So that'll be minus b minus negative b, that'll be positive b, plus or minus square root of b squared, that's negative b squared, that'll be 9, minus 4 times a, which is 5. Yes, yeah, correct. 4 times a times c, that's negative 2. Over 2a, that's 2 times 5. So then there's this minus, that'll be a plus. So x is 3 plus or minus, that'll be square root of, so 4 times 5, that's 20, times 2, that's 40, that'll be square root of 49, right? Over 2 times 5, that's 10, so that's 3 plus or minus square root of 49, that'll be 7, right? Christina, well, you see with the with the examples later, you see it's not that bad. I mean, of course, when first time when you see this like vertical and horizontal asymptote, it's scary, but you'll see. It's with a little bit of practice. As I said, it's this graphing rational functions. It's not easy in general, okay, because of this vertical and horizontal asymptote. But we'll see with the examples. I hope things will get better. But let's just try to find those vertical asymptote and horizontal asymptote. So yeah, square root of 49, it's 7. This is over 10. So then your x gonna be 3 plus 7 over 10, or so that'll be 10 over 10. That'll be 1, or x is 3 minus 7 over 10, so that's negative 4 over 10. You reduce your fraction, right? You have to divide the top and the bottom here. You can divide both by 2. So that will be negative 2/5, right? This is negative 2/5. So we got, sorry, I got my solutions. I have x equal to 0. I got x equal to 1 and x equal to negative 2/5. So yeah, the vertical asymptotes here, they're going to be just, so the answer, so vertical asymptote are we got 0, so x equal to 0. Just for the notation, guys, here we are talking about lines, not like x-intercept. You would use like the points notation, like x coordinate, y coordinate. Here for the vertical asymptotes, we don't use points notation, right? This is our lines, right? So the answer here is just like x equal to 0, x equal to positive 1, and x equal to negative 2/5. Okay, so this is again different from the x-intercept. I mean, in terms of notation, we don't use the points notation here. Just write x equal to 0, you know, etc., etc. So that's a vertical asymptote. Yeah, this is for no vertical asymptote. You can have like more than one. Here, like we have like 3 vertical asymptote. The horizontal asymptote, you cannot have more than one. Horizontal asymptote, yes, you're right. So for the horizontal asymptote, at most you can have 1 horizontal asymptote, but the vertical asymptote you can have more than one for sure. So before the horizontal asymptote, guys, let me just explain. So what do we mean, or what does it mean to have x equal to 0, x equal to 1, and x equal to negative 2/5 as a vertical asymptote? So the idea is the following. So in the graph, and of course, I'm going to explain this in more details next time with the exercises, but the idea is we're going to have like, so in the graph, of course, you need x equal to 0. This is my x equal to 0. This is my x equal to 1. And this is my x equal to negative 2/5. So we're going to have vertical asymptote. So that's like vertical line. So here's my vertical line passing through this x equal to 0. This is x equal to 0, x equal to 1, and here x equal to negative 2/5. So these lines, they're going to be vertical asymptotes. It means that for the graph, so the graph is going to be as close as we want from these lines, but it doesn't intersect these lines, right? So you're going to have something like this here. So we're going to, you know, your graph is going to be as close as you want from this line, but it never touch the vertical asymptote, right? So we're going to have something like this here. Same thing right here. Both sides, of course. Or so the last line here, the last vertical asymptote. So you're going to have something like this, you know. Okay. And again, there will be no intersection, right? So just keep in mind here or here or here, there will be no intersection. You can get as close as you want from the line, but there will be no intersection, right? It doesn't cross the line. So that's for the vertical asymptote. Now for horizontal asymptote, in 30 seconds, guys, I'm sorry about this. So the horizontal asymptote, so we need to compare. So we need to compare degrees of P and Q, compare degrees of P and Q. So in this example, degree of P, where is it? So P is, degree of P is 4, degree of Q is 4. So they have the same degree. And in this case, when you have the same degree, so this is like the case number 3, right? This case number 3. Degree of P is equal to the degree of Q, then the horizontal asymptote would be the leading coefficient of P over the leading coefficient of Q. So that will be the 2 This is the leading coefficient of P over 5, the leading coefficient of Q. So that will be 2 over 5. All right, so let me just 10 seconds. I'm gonna just write down here the answer. So the horizontal asymptote is, it's gonna be y equals to 2 over 5. Okay, so like in your graph, so 2/5 here, this is y, 2 over 5, this horizontal asymptote right here, and then the graph is gonna, as I said, at infinity, is gonna be very close to your horizontal asymptote, but never touch actually the horizontal asymptote. All right. Anyway, guys, thank you for listening. I'm sorry I went over time. I'm gonna stop here. So next time we'll discuss, of course, how to graph, use all these informations to graph f of x, and we're gonna practice it a bit. All right, guys, thank you for listening, and I will see you next Monday.
Okay, Chuck, thank you.
Thank you, everyone, and I will see you on Monday. Take care. Thank you.
Professor.
Yes, Matthew. Yeah.